Good evening. Welcome to lecture 10 of Thermodynamics course conducted by NPTEL. And this is week 9 revision and assignment questions being discussed. So we'll start with the revision questions. First, the question is it true that the summation of y of I, that is a different species, is equal to 1 for a mixture of gases? The summation is over I, which denotes each species in a gas mixture. Okay, so here the y of I represents mole fraction, right? So mole fraction, summation of mole fraction over all the species in the mixture of gases should be equal to 1. Yes, that is true. How? That is the second question. Okay. Now, next is this y of I is mass fraction. Okay, so they are asking, is it always true that for a gas mixture, capital Y of I summation is equal to 1? Okay, so this mass fraction, uh, yes, it also accounts for all the species in a gas mixture, so that is also true again. Okay, so the answer is true. Now, a person says that Dalton's law of partial pressure is that the sum of the partial pressure of each component in a gas mixture equals the pressure of the mixture. Is this a statement complete and or correct? Okay, so Dalton's law states that the total pressure is the sum of partial pressures, and the statement says sum of partial pressures equals to the pressure of the mixture. So that is completely correct about Dalton's law. So yes, this is a correct statement. Okay. Next um, is it true that Dalton's law is generally accurate at low pressure, and that Amagat's law is better at high pressure? Yes, because Dalton's law is accurate at low pressure. Um, and low pressure is where the gases behave ideally. While in Amagat's law, sum of volume is what we are considering, and that is better at high pressure. So that is correct. Now, which of the following relations are correct? So, partial pressure ratio with the total pressure is equal to mole fraction. So, this is Dalton's law. So, that's correct. Now, the next one is not. So if the first one is correct, then the second one is incorrect. Then third one is temperature ratio with the total temperature is equal to mole fraction. So if you are taking Charles' law, P I mean pressure is directly proportional to temperature. So if you are taking the pressure ratios and you are getting number of moles, the temperature ratio should also give you the mole fraction. So but the thing is, okay, so but you should not think like that, because temperature of all the species in a gaseous mixture will be constant when we are considering that mixture is in thermal equilibrium. Thermal equilibrium, Ti equal to T. So this is also not correct. Then you have got this mass of the species to total mass. This is mass fraction. This is capital Y of I, not small y of I. So yes, that is also wrong. Then the fifth one is correct. Okay, because this shows mole fraction, this shows mass fraction. So that's about the answer. So answers, correct options are A and E. Next is write the relation for the constant pressure, specific heat of a mixture, joule per kilogram Kelvin of gases in terms of either mass or mole fraction of the constant gas. So for mass fraction, we have to take Cp of mix equals sigma y of I times Cp of I. Okay. And for mole fraction, Cp of mix is equal to summation of small y of I times Cp of I by mass of mixture. Okay, so that is like molar mass. Molar, okay, this is molar mass of mixture. Next is derive the relation between mole fraction and mass fraction. So the answer is mole fraction, sorry, mass fraction is equal to number of moles times molar mass. Okay, number of moles times molar mass by total molar mass of the mixture. So this is how it will be coming. I'll write it over here again. 9.7. Y, capital Y of I equals to Y of I Mi by M of mixture. Now, next question, 9.8. Derive entropy change. Okay, so it is desired to calculate the change of entropy of a species in a gas mixture which undergoes a process from state 1 to state 2. The relation for this purpose is given below. Derive it from the first principles. Okay, so we have to derive entropy change for a species. So entropy change formula, we know it is uh, delta S equals to Cp log T2 by T1 minus R log P2 by P1. That is what is given here. Okay. So what we have to do is, it's per species. Per species means partial pressures will be P of I. It will be coming as Y of I times P. So if you are substituting this in the equation, you will be getting the uh, per species entropy change. Then next one is entropy generation during mixture is the question. Okay, like two gases A and B, both of them are at a same pressure and temperature, are mixed without heat or work transfer. The final pressure and temperature are small p and, okay, again p and t respectively, are same as the initial state. Okay, show that the entropy generation during the process is given by the relation below, and that show that it is greater than 0. Okay, so when mixing gases at same temperature and pressure, entropy generation is due to mixing. Okay, and we can use this relation delta S equal to minus nr sigma yi log yi. So yi is greater than, I mean less than 1. So log yi is negative. So delta S is going to be positive. Okay. So that is how we are finding it. From here, yi is less than 1. So log yi is negative. So negative and negative, it will become positive. So delta S is going to be a positive quantity. So greater than 0. Next is, in the previous problem, the state is 2 bar 450 Kelvin and 1 mole of oxygen is mixed with 1 mole of helium. In another case, with same states, 1 mole of oxygen is mixed with 1 mole of carbon dioxide. A person says entropy change will be same for both process. Is this true? Okay, so oxygen and helium, and then second case is oxygen and carbon dioxide. So entropy change depends on mole fraction. If the moles are same, then yi value will be same. But helium and carbon dioxide, they are having different molar masses, and formula only depends on mole fraction. So entropy change, since the mole fraction are the same, so the entropy change is going to be the same. So the statement is true. Okay. So this helium and carbon dioxide, even though their masses, molar masses are different, but the here what they have given is mole fraction or number of moles. So the mole fraction is going to be the same, and the equation for entropy generation during mixture uh, depends only on mole fraction, or yeah, mole fraction of the species. So entropy change will be same for both the processes. One of the species in a gas mixture is methane, which is 12% by mole. Calculate the methane mass per kilomole of mixture and its mass per kilogram of mixture. So mass fraction and mole fraction we have to find. Okay. So methane is 12% by mole. So mass per kilomole will be 0.12 times. Methane molar mass is 16 kilogram per kilomole. Okay. So that is equal to 1.92 kilogram per kilomole. And then mass fraction is 1.92. So 1.92 by, I'll write it in another page. Okay. Okay, so the question number 9.11. So methane is 12%. So mass per kilomole is 0.12 times 16 kilogram per kilomole of CH4 molar mass. Okay, that is CH4 molar mass. That is equal to 1.92 kilogram per kilomole. Now we have to find mass fraction. That is equal to 1.92 by mass of the mix. So one second. What is it written? Species, one of the species in the Okay, it is written one of the species is uh, methane. But what about the other species? That is not given, right? So assuming something like, for example, M mix will be uh, mass of methane CH4 plus mass of rest of the gas, whatever it is. So suppose this Mg is, so here it is given 0.12 or 12 percentage of the gas is methane. So rest 0.88 will be the other gas times the molar mass of the gas we have to take. So that is how we are going to calculate molar mass of the, total mass of the mixture. Next question. In a combustor, 1 kilogram per second of a gaseous fuel is mixed with 14 kilogram per second of air. The mixture flow into a burner. Which law do you recommend for analyzing this mixture, Dalton's law or Amagat's law? Okay, so as we have said earlier, Amagat's law is better, but combustors typically operate at high temperatures and pressure. Okay. Air and fuel are usually modeled as ideal gas. So, in that case, we can use Dalton's law. Okay. And here, this flow rates are given, um, and that is like mass per second kind of unit is given. So, mass fractions are used. Okay. So, what we are seeing here is Amagat's law is for pressure, high pressure. Dalton's is for again ideal gas assumptions, uh, and if it is like low pressure compared to the critical points, again Dalton's law will be preferred. So uh, comp- like thinking about the ideal gas behavior, we will prefer Dalton's law. Okay, so then next question. A person calculates the constant pressure, specific heat. Okay, so person calculates the constant pressure, specific heat of a mixture of gases as 1.27 kilojoule per kilogram Kelvin. The constant pressure, specific heat component of each constituent gas is less than its value. Is this calculation in error? Okay, so specific heat of mixture is higher than the constituents. So if each Cp of I is less than 1.27 kilojoule per kilogram Kelvin, but the mixture Cp is high, that is impossible because Cp mix is the weighted average that we have to take. Okay, so if all components have lower Cp, the mixture can't have higher. So the calculation is in error. Yes, it is wrong. It is error. Next is 9.14. A mixture of gases undergoes an isentropic compression process in a cylinder piston arrangement. Can this process be modeled by the relation PV raised to K equal to constant? So isentropic process for mixture with PV raised to K equal to constant. So for mixture, K is specific heat ratio of the mixture. So if the process is isentropic and gas is ideal, then yeah, for sure we can use this relation, uh, where K equal to, okay, K equal to Cp mix by Cv mix. Okay. Next is a mixture of gases undergoes a uh, heating process. Write the mixture equations for conservation of mass and first law. Okay, so conservation of mass is sigma mi equals to constant, and first law is Q equal to delta U plus W. That is how it will be happening. So mixture equation means you have to take specific heat, specific internal energy, and specific work, and then you are going to multiply with the mass, and that mass comes from Yi times molar mass of the species. So that is how you are going to incorporate this into this equation, first law. Second is, consider the unsteady uniform uh, uniform flow process for a pure substance. How can the formation for mass and energy conservation be extended to a mixture? Example, a cylinder containing a mixture of gases is being evacuated. Okay, so we will be first taking conservation of mass, which is like, okay, so conservation of mass we will be taking like dm by dt equals sigma m in minus sigma m out. And energy conservation we have to take du by dt equals to sigma m in h in minus sigma m out h out. So we'll be taking flow rate because it is time rate equation. Okay, then yeah, for energy again Q will be there, and work will be subtracted. So for mixture again we have to take this M as mol. I mean, um, for the each species, that proportion uh, or the properties will be based on the mixture composition. So you have to take that into consideration. So individual MIs will be coming, that will be taken in this form. Okay. Now in the previous problem, consider a unsteady uniform flow process where one species, say hydrogen, is being filled into a cylinder which has a mixture of nitrogen and hydrogen. This too is an unsteady and uniform flow process. Write the equation for this process. Okay, so what are we supposed to do here is the equation for mass conservation and energy conservation. Both we have to consider um, for incoming hydrogen and existing nitrogen and hydrogen mixture. Okay, so this dm by dt will only have incoming hydrogen flux. Okay, and then energy will be having this existing one. Okay, change in energy if we are taking, that will be only due to hydrogen. So du by dt equal to m dot h2 uh, in times h2 in plus q minus w. Okay, I write it over here. So du by dt equals to MH2 in HH2 in minus plus Q minus W. Okay, so that is how we have to calculate it. Now, how can one calculate the work required to separate a mixture into its constituents? So, work to separate mixture will be the Gibbs free energy uh, of change in mixing. So, that is like W equal to minus T delta S. So, using the entropy of mixing formula, we can find it. So, W equal to minus T delta S. So, delta S is due to mixing. Now, is it true that all mixtures of gases behave as ideal gas? No. Uh, so, ideal gas behavior uh, will vary if it is two reacting gases. For reacting gases, it deviates, and also temperature and pressure. Okay, that also matters. So, for high pressures or low temperature, real gas behavior will be happening. Next is a drop of volatile fluid is uh, dropped into a closed vessel containing a gas, different chemical than that of the drop. The drop evaporates and a gas mixture is formed in the container. The composition of this mixture is desired. Write the equations in terms of the properties of the drop. So 9.20. Evaporation of drop in a gas. Okay, so it is a drop of a volatile fluid is dropped into a closed vessel containing a gas. So drop evaporates and the gas mixture is formed in the container. So evaporation of a drop in a gas, the mixture composition depends on the vapor pressure of the liquid and the total pressure. So using Henry's law, uh, or depending on the substance, like for ideal, we will be taking P total, or the total pressure equal to gas pressure plus vapor pressure, and vapor pressure will be nRT by V. Okay, so that is how we will be calculating. Now, is it true for a mixture of diatomic gases, the specific heat ratio K equal to Cp by Cv equal to 1.4? Yeah, yes, for diatomic gases, we are taking K equal to 1.4 only. So that's true. Now, can the compressibility factor for a gas mixture be greater than the largest of compressibility factors of the constituent gases? Uh, so they are talking about Z mix. So Z mix um, exceed the largest of Z of constituent? Yes. If the interactions between molecules are causing more deviation from ideal, then obviously it can have higher compressibility. So Z mix can be greater than Z of I. Max of Z of I. It can be. Okay. Next is nitrogen flows through an isentropic turbine and undergoes a certain temperature drop. An engineer wants to reduce the mass flow rate while keeping the same temperature drop and same specific work output. She has the choice of mixing helium or hydrogen. What is your recommendation for which gas should be mixed? So, engineer wants to reduce uh, Okay, reduce mass flow rate while keeping temperature drop and work. Specific work is W equal to Cp times delta T. So to keep W same with lower mass flow, we need to have higher constant pressure, specific heat of constant pressure. Constant pressure, specific heat. So helium has a higher Cp than nitrogen, and hydrogen also has higher Cp. So now we have to compare helium and hydrogen. So uh, Cp for helium is monatomic, so that is 5 by 2 R, and hydrogen is diatomic, so that is 7 by 2 R. But Cp is higher for hydrogen since smaller mass is lower. So mixing with hydrogen would increase specific heat, allowing lower mass flow for same work. So we recommend hydrogen. Okay. So the choice of mixing will be hydrogen. Okay. Now, next question. The atmosphere of Neptune is considered to consist of 83% of hydrogen, 15% of helium, and 2% of methane. Its temperature is estimated to be about 60 Kelvin. Can the equations developed in this section can be used for calculating the specific heat or gas constants of this mixture? Give supporting arguments. So Neptune's atmosphere, we can take it as like a ideal gas behavior. First of all, we have to assume ideal gas behavior. Then at 60 Kelvin and high pressure, uh, we have to we have to understand that 60 Kelvin is a very small temperature, and high pressure means it is real gas behavior. Okay, so we cannot take ideal gas equations over there. Okay, so if we are taking ideal gas behavior only, then we can calculate using specific heat or gas constants of the mixture. Okay, but another thing is we can take it like hydrogen, helium, and methane, they don't react with each other. In that manner, we can take like this is an ideal gas mixture. In that manner, we can take it, but with temperature and pressure, we cannot consider this as a ideal gas scenario. So you cannot calculate using ideal gas equation. So next is during pandemic, oxygen enriched air was given to patient. In one technique, oxygen concentrator, the nitrogen was absorbed on a certain salt. If 70% of the nitrogen by volume were to be absorbed, what will be the oxygen concentration in the enriched air? Okay, so usually uh, the air has 71, I mean, sorry, 79 percentage of nitrogen and 21 percentage of oxygen. If 70% nitrogen is absorbed, remaining is into, we will be having zero point 0.3 times 79%, which is equal to 23.7%. Total volume is O2 plus into remaining equal to 21 plus 23. 44.7 percentage. Now oxygen concentration will be what? 21 by 44.7, which is equal to almost like 47%. Okay, this will be the answer. Now, assignment problem. Question number 1. Dry air is a mixture of 78.09% by volume nitrogen, 20.95% by volume oxygen, 0.93% by volume argon, and 0.04% carbon dioxide. Calculate the mass and mole fraction of each of these components. Show that if only major components, that is nitrogen and oxygen, are considered, then air can be expressed as O2 plus 3.76 N2. Okay, so show air as O2 plus 3.76 N2. So given volume fractions are, N2 is 78.09, oxygen is 20.95, and ratio, if you're taking, we will be getting 1 is to 3.76. So the first one is correct. Okay, you just take the percentage ratio, you will be getting the same stoichiometric ratio. Then next is not stoichiometry exactly, but yeah, mole fraction ratio, you'll be getting like this. Calculate Cp and R at 1 bar 300 Kelvin. So Cp for nitrogen and oxygen, you have to take from the table. So at 300 Kelvin, nitrogen Cp is around Cp equal to 1.039 kilojoule per kilogram Kelvin for nitrogen, and Cp for oxygen is 0.918 kilojoule per kilogram Kelvin for oxygen. Okay. So R value, if you have to calculate, you have to use this formula. R mix equal to R universal by M mix. So for finding M mix, you have to find mole fraction. So how to find mole fraction? Just divide these percentage by 100. So it is 0.78. This is 0.2095. Then multiply it with the mole fractions. So nitrogen is 28, oxygen is 32. And molar mass you have to multiply. So that will give you the, and then add it together, you will be getting the mass. So mass fraction you will be getting, and then you have to calculate with this formula for R mix. Okay. Now repeat part B for the following state for different pressure and temperature. Okay, so you have to find Cp from these you have to find Cp from the table for these temperatures and pressure, and then you have to use it for the calculation. Okay, that's about it. Then second question, consider moist air as a mixture of two pure substances, that is dry air, they are saying it is a pseudo pure substance, and water, which is in vapor form. Consider a state where moist air at 1 bar and 25 degree contains 0.025 kilogram water per kilogram of dry air. Now we have to find what is called as viscosity of steam or the moisture content. Okay, so mass and mole fraction of each component, constant pressure, specific heats for dry air and moist air, and then calculate the density of dry air and moist air. Okay, so it is given 0.025 kilogram water per kilogram of dry air. Mass fraction you have to find, like total mass is 1 kilogram dry air plus 0.025 kilogram of water, that is 1.025, and then y of air will be 1 by 1.025 and y of water will be mass fraction of water will be 0.025 by 1.025. Now mole fraction we have to find. So mole fraction, mass of air will be 28.97 and mass of water will be 18. So moles you have to calculate like 1 by 28.97 and 0.025 by 18 for water. So then add it together, you will be getting total number of moles. Then mole fraction you have to divide it by total number of moles, like individual species mole by total number of moles. So you'll be getting mole fraction. That is how you will be calculating this too. Okay, I'll write it over here. Nine point two. Given 0.025 kilogram H2O per kilogram of dry air. So mass fraction you have to write like total mass equal to 1 plus 0.025 equal to 1.025 kilogram. Now y of air equals to 1 by 1.025 and y of water equal to 0.25 by 1.025. Now mole fraction, for that we have to use these data. M air equal to 28.97 and M water equal to 18. So moles of air equals to 1 by 28.97 and moles of water equals to 0.025 divided by 18. Okay. Now total mole equal to, you have to add moles of air plus moles of water. And then you have to calculate mole fraction like this: moles of air by total moles, and the other way around also. For water, similarly, we have to find y water equal to moles of water by total moles. Now Uh, Next question was compare the constant pressure, specific heat of dry air and moist air. So Cp of moist air will be Cp mix. Okay, so I'll write it over here again. This is A part. A part. No, B part is Cp of moist air equal to Cp mix. First we have to find Cp mix. Cp mix equal to Y air times Cp of air plus Y H2O times Cp of vapor. Now Cp of air is 1.005 kilojoule per kilogram Kelvin, and Cp of vapor equals to 1.872 kilojoule per kilogram Kelvin. Now Cp of mix will be the sum total of these. You have to just find Y air and all those values, you have to plug it in and you will be getting that. Okay. And then the next question. Next part of the question is calculate the density of dry air. Okay. So I'll write it over here. C part density. So dry air density equals P by R air times T. So R air equals to 0.287 kilojoule per kilogram Kelvin and T is 298 Kelvin. So dry air density equals to 100 kilopascal by these value. Okay. Now for moist air, R mix equals to Y air times R air plus Y H2O times R vapor. That you have to find. Okay. So R mix you have to find like this. Then density equal to P by R mix times T. Okay. Now question number 3. 3 liters of water is mixed with 1 liter of ethylene glycol at ambient temperature and pressure. Calculate the mixture density. Okay, so density equal to total mass by total volume. So water mass you have to take, glycol mass you have to take. Okay, glycol mass you have to take. Then mass of water and the mass of glycol you have to take. Then add it, that you will be getting total mass, and volume will be 4 liter. So if you divide it, you will be getting the density of the mixture. Why we can do this thing is because glycol and water does not react with each other. So they are ideal mixture. Okay. Next is a rigid vessel contains a mixture of nitrogen 20 kilomole, oxygen 2 kilomole, and hydrogen 1 kilomole at 300 Kelvin and 2 bar pressure. Calculate the volume of tank using each of the following method. Ideal gas equation of state, Hayes rule, compressibility factors and Amagat's law, and compressibility factor and Dalton's law. Okay, so rigid vessel with nitrogen, oxygen, and hydrogen. Ideal gas law, everybody knows it is. Okay, 1 second. V equal to, so we have to calculate the volume, right? Yeah. So V equal to nRT by P. So that is the equation that we are using. N is directly given, R is given, T is given. I mean, R everybody knows, T is given, P is given. Directly you can calculate. Case rule, so we have to use zero critical T and P. C mix equal to sigma yi T TC of I and PC of mix. Okay. Okay. P of P of I. If you take that, wait 1 second. So C mix equal to this one for temperature. Yeah. For temperature, this will be the one. And for pressure, you have to calculate using YA PC of I. Okay. So critical temperature of mixture, we have to use this equation. And critical pressure of the mixture, you have to use this one. Now we have to find the critical temperature and pressure of each of the species present in the vessel. Now compressibility factor. Compressibility factor and Amagat's law. Amagat's law will be V I equal to Z I N I R T by P. Okay. And total V will be V equal to summation of VI. That's it. Then for each of the species, you have to find VI using Amagat's law and then sum it over. Now, Dalton's law with compressibility, we have to find PI first using NIRT by V. Then P equal to sigma PI. Then we will be calculating V equal to nRT by P. Okay. Now, fifth question. Superheated R410A flows in a tube. Over a certain length of the tube, the pressure is almost constant at 2 bar and it is cooled from 50 degrees Celsius to 40 degrees Celsius. Calculate the heat transfer rate from the mixture. Composition of R410A is 50%, R32 difluoromethane CF2H2 and 50% of R125 pentafluoroethane, that is C2H5HF5. Okay, so CP values are given for both the refrigerants. Now we have to calculate the heat transfer. So heat transfer rate is Q equal to MCP delta T, and okay, mass. Okay, the composition is given 50%, 50% is given, and CP value is also given. So CP value you have to take it like 0.5 of CPR32 plus, so CP of mix we have to find, right, plus a 0.5 of CP of R125. Okay, in that manner we will be getting CP of mixture. Delta T is already given. Uh, Now we need the mass flow rate. So mass flow rate is, if it is given, then we can calculate it directly. Here it is not given, so you cannot calculate. But this is the method. Now, sixth question. Rigid vessel of 10-liter capacity is initially evacuated. It is filled with nitrogen until the pressure is 500 kilopascal. It is then filled with oxygen until the pressure is 800 kilopascal. Finally, carbon monoxide is added until the pressure reaches 900 kilopascal. Throughout the process, the gas being filled is at 300 Kelvin and the vessel is also maintained at 300 Kelvin. Calculate the mass of each gas in the vessel and vessel pressure and temperature after each gas is filled. So what they are trying to say is ideal gas law can be applied because gas pressure is somewhere in the normal range. Temperature is not varying. So only due to mixture this entropy is induced. There is no reaction or anything. They are saying all the statement to Im- imply that okay, ideal gas law can be applied. So rigid vessel is filling. Initially it is evacuated. Nitrogen was filled to 500 kilopascal, then oxygen up to 800 kilopascal, and carbon monoxide up to 900 kilopascal. So each gas's pressure adds to the total. And a rigid vessel, so volume is constant. So nitrogen partial pressure will be 500 kilopascal, and so you can calculate mole moles number of moles of nitrogen from this pressure, like PV by RT. If you calculate, you'll be getting nitrogen moles. Similarly, oxygen is added to nitrogen, so that extra 300 kilopascal is due to oxygen. Again, you can calculate the number of moles of oxygen. Then carbon dioxide also, monoxide also the same way you can calculate. Then total mass you have to multiply with the molar mass of the species, and then you will be getting the total mass. Okay. Now seventh question. A cylinder piston arrangement contains a mixture of 1 kg of carbon dioxide and 2 kg of nitrogen at 100 kilopascal and 300 Kelvin. It is heated, and during this process, the piston rises until the volume is tripled. Determine heat transfer to the arrangement, work for the piston, and entropy change for the mixture. So, cylinder with carbon dioxide and nitrogen heated until the volume triples. So process is likely to be constant pressure. If piston rises freely, pressure may be constant. Okay. Now mass of 1 kg of carbon dioxide you can calculate, and 2 kg of nitrogen also you can calculate. Okay. So total mass is 3 kg. And number of moles you can calculate from given mass by molar mass for both the species, and total number of moles also you can calculate. Now initial status P1 is there, T1 is there, V1 we can calculate. The final volume is 3 times the initial volume. Now if pressure is constant pressure, then P2 is equal to P1. Now temperature you have to find. P2 is there, V2 is there, R is there, N is there. You can easily find T2. Now heat transfer, we want to find delta U plus W. Delta U you can find from molar mass and constant volume, CV value, specific heat, constant volume specific heat of carbon dioxide, and delta T, MCV delta T. So MCV delta T plus MCV delta T of nitrogen. One is for carbon dioxide, one is for nitrogen. Then CV you have to find from the tables. Then you can find delta U, and W you can find from P delta V. So V2 is found, V1 is found. You can find delta V. P is constant. We'll be getting Q, that is delta U plus W. You can easily find. Okay, so entropy change also direct equation only. You can easily find that. Okay. Now, if you want, I can write it over here. All calculation I can write. 1 second. Okay. 7th question. So, constant pressure process. Masses are given. CO2 1 kg and nitrogen 2 kg. Okay. Then M of this is 44. This is 28. Total mass equal to 3 kg. Now N of CO2 equal to 1 by 44. N of nitrogen equal to 2 by 28. Then you can find total N. Okay. Then what we have to do is initial state P1 equal to 100 kilopascal, T1 equal to 300 Kelvin, V1 equal to nRT1 by P1. Okay. Now, final state, what is the only change happen? P1, P2 equal to P1. Okay. V2 equal to 3 times V1. So whatever value you are getting from V1, you just substitute it here and calculate V2. Then we have to find T2, which is equal to P2 V2 by NR. Right. So that is how you will be finding T2. And the second part was heat transfer. Heat transfer equal to, sorry, this is B part. This is A part. Q equal to delta U plus W. So delta U equal to MCO2 CvCO2 delta T plus M into Cv into delta T. Those values we can substitute. Then W equal to P delta V. Okay. Then if you substitute these two values to this first law, you will be getting Q also. Then entropy change, delta S equal to MCO2 CpCO2 log T2 by T1 minus R log P2 by P1. Okay. This is one term. Then next term is Mn2 times Cp into log T2 by P1 minus R log P2 by P1. Okay. Now P is constant, you can take it outside and that R term will be gone. For P2 and P1 is log 1 is 0, so this will be going to 0. Only these ratios will exist. Temperature ratios will be existing. That is about delta S. Now, next question. Two high pressure tanks are connected by a pipe with a valve. Initially, the valve is closed and one tank contains 10 kg mixture of 60% helium and 40% oxygen on mole basis at 100 kilopascal and 35 degrees centigrade. Tank B contains 5 kg of hydrogen at 4 kilopascal and 10 degrees centigrade. The valve is opened and the gases are allowed to mix. Calculate the volume of tank A and tank B. Determine the final pressure and temperature of the system when the entire arrangement is well insulated. Determine the final pressure and temperature when 2000 kilojoule of heat transfer occurs to the tanks during the process. Okay, so this is the final question. So tank A, they are saying 10 kilogram of helium and 40% of oxygen. 10 kilogram mixture, 60% of helium and 40% oxygen. Okay. So Na you can find Na equals to 0.6 by 0.6 times 10 by 4 plus 0.4 times 10 by 32. This 10 is the total mass of the mixture, which is equal to 1.5 plus 0.125 equal to 1.625. So total moles in Na, okay, 10 by m of mix of in A. Okay, m of mix in A equal to 0.6 times 4 plus 0.4 times 32 equals to 2.4 plus 12.8, which is equal to 15.2 gram per mole. Okay, so Na equal to 10 by 0.0152, this is kilogram per mole, equal to 657.889 mole. Now, for tank B, Va equal to NaRT A by Ba equal to 657.89 times 8.314 times 308 by 10 to the power 6. You will be getting some value over here. This is for volume A. Now, tank B, NB equal to 5 kilogram by 2 gram per mole, which is equal to 2500 mole. Volume of B equal to NB RTB by PB. You can find it. Now, final pressure and temperature, if you want to find, then total moles equal to this one plus this one. Okay, Na plus Nb. Then total volume. Okay, that is also Va plus Vep. Now energy conservation, U total equal to UA plus UB. U equal to NCVT for ideal gas. So we are going to find why we are doing this thing, to find T. Okay. So Cv equal to 3 by 2 R for helium, and Cv equal to 5 by 2 R for hydrogen, oxygen, and Cv equal to 5 by 2 R for hydrogen. So UA equal to NHE Cv He, Cv of He Ta plus NO2 Cv of O2 Ta equal to, you have to find the value. Or you keep it like that only. We will cut it off later. And so NHE and NO2, you have to substitute, and you will be getting UA. Okay, UA value you can find from here. Then R you substitute, Cv and Cv of He and O2 you'll be finding. Then UB again, NH2 CvH2 TV you will be finding. So U equal to UA plus UB. Okay. Now, now you can solve for T. Then final pressure P equal to N total RT by V total. With heat transfer means again U total equal to UA plus UB plus U. Okay. Then the temperature will be different because U total expression has got a heat top value. Then with that temperature you can find final pressure for heat transfer case. Yes, so that's all for today's lecture. Hope it was very helpful for solving the week's assignment. Thank you.